Okay, so let me start, okay? Just to emphasize that whatever I'm going to cover today and also on Friday in the first hour will not be appearing in the examination. So this is something confirmed. So I've chosen a different topic this year because some of you made a wish to me. And indeed, it's a very popular topic nowadays. It's about doing calculus on function whose domain or the codomain is the space of matrices. I spent a little bit of time looking for references, and they're, no offense, they're all very poorly written. And then, but it's getting more important. And then so I decided to write my own notes, and then the notes were written in a way such that the notation is more consistent with classical calculus and also in my course. When I finished writing my notes, I actually posted part of the notes on my own social media. Then one of my, you may say previous student, okay, it's 学弟, okay, 学弟, but then we're 6-year difference, okay, and I supervised his project once upon a time, so I call him my student. He replied to me, he's an engineer, okay, this is my conversation, and then let me highlight the thing, okay. So basically, it's weird that he never have an actual course in matrix calculus, but then it seems that when you get to your 3rd year or 4th year, he will just assume you to know a little bit. And I think this is exactly the kind of story I hear from most of you, okay? That at certain stage, your professor, no matter from economics or from computer science, they can't assume you know how to do it. And for your information, he has an undergraduate degree in engineering, and he's now working in Meta, okay, in Seattle. So, in any case, okay, so let me start. I'm going to start with reviewing a little bit about classical calculus. So something you learn in Calculus 3, multivariable calculus. But then at that time, okay, you focus on so-called scalar value function whose domain is Rn. So the domain is Rn, and it goes to R. Then the first thing you learn is so-called partial derivative that measure the rate of change of the function with respect to just one of the variables. Then the next thing you learn in Calculus 3 is to put all these partial derivatives together and form a so-called gradient vector. So I'm using a more mathematical notation for gradient vector that is upside down triangle f, and then I put a variable. So in this case, the variables are x1 to xn. I put it in the column here, okay? So in calculus, usually you write as upside down triangle x, okay, something like that. But then I just fulfill a more conventional mathematical convention that is putting the variable at the bottom. The next thing is, in Calculus 3, you put your gradient vector as a row vector, but then now you grow up, you know everything should be a column, so I put transpose. Okay, I put transpose. So my gradient is actually a column vector, just for convenience. And I mentioned that at the end of the day, I want to study how to do calculus on such that the domain now is not Rn anymore, but the space of matrices. But before I do that, let me review, okay, a little bit about the space of matrices. Something you learned before, but it's going to get very important. So let me recall the definitions, okay? So to us, okay, we will write M times Mr to be the vector space of m by n real matrices over R, over real numbers. And we have to know that, okay, from one of your homework and also in the lectures, okay, we can turn this space into an inner product space. And the inner product is quite funny. If you have two matrices, then how do you take the inner product, okay? One way to do it is to take A transpose B and take the trace, okay? So what is the trace? The trace is the sum of the diagonal entries. So, and then we call it, now we give it a name. The name is called Frobenius inner product. Then of course, once you have inner product, you define the norm. The norm is just the square root of the inner product with itself. So the trace of A transpose A, and then take square root. Now, at first, you may find this definition of Frobenius inner product a bit funny, but think about the special case when n is 1, i.e. you're considering column vectors, then the Frobenius inner product becomes just dot product. So you may regard, okay, the Frobenius inner product is such a lecture generalization of dot product, but now on matrices. And sometimes when I'm lazy, because we will be working with just Frobenius inner product in this week, so instead of writing the bracket with an F, I will just omit the F sometime. Okay, if you forget, I always means it's the Frobenius inner product. And last but not least is there's a quick way to compute these traits. Basically, it's really like a dot product, okay? So you just take the coordinate-wise, okay, entry-wise product and sum everything. But because now you have a matrix, so you need to sum over I and also sum over J. So in other words, the Frobenius inner product is simply the ordinary dot product. But then now you just imagine yourself, you're writing the matrix as a very long vector. So essentially, you do dot product on matrices, okay? But then we write in a funny way. So nothing about calculus yet, okay? These are the things that we've seen before, but now we recap and formulate notation. Then the next one I'm going to do is actual calculus. So how to define derivative? Now it's a term. Now if you notice in your calculus 3, okay, if you've done YC 微积分 3, okay, then you will realize that we have taught you what is differentiable function in multivariable, but we never use the word derivative, okay? We try to hide it from you, and one of the reasons why is to define derivative in multivariable setting, you need to know a little bit of linear algebra. So let's have a look on. So now we study, we focus on scalar value first, okay, and then we'll work on more general setting later. So we have scalar value function, and as such now the domain is a space of matrices. And let me define for this kind of function, what does it mean for to be its derivative, okay? Given a function whose domain is a space of matrix, then how do I define its derivative? Definition 15.2.1. If you have such kind of function and assume it's differentiable, so I'm not going to explain this word, I put a footnote. So differentiable just means what it means in calculus 3, but I assume everything is differentiable today, okay? And then what does it mean by the derivative of this function? First of all, derivative, the notation, I call it dfx, okay? And what is derivative? Derivative is actually a linear function, linear map. From where to where, it's the same as the original function. From the space of matrices to R. But of course, when the codomain is R, there's another name for linear map. You also call it a linear functional. You can regard that as an element in the dual space, okay? But the point is, what is derivative? Derivative is itself a linear map. And that is the reason why in calculus 3, we don't teach you what is a derivative of a multivariable function, because we don't expect students to know what linear maps are. And what is so special about this linear map? This linear map will fit into an equation of the form f of x plus h minus fx. So something look like what you learned in calculus 1, how to study derivative. And then where does the linear map come from? The linear map comes from here. But then they're not equal, okay? You need to up to some HOT, which HOT is not hard, but higher order terms. So in other words, the derivative can't capture all, because it's itself a linear map, so it captures all the linear terms. So it captures the linear terms in H, okay? In H, okay? I can formulate what does it mean by higher order terms a little more carefully. It's in the remark on the right hand side. So I say higher order terms, it means those terms of second or higher orders. Or if you want to really write carefully, it means that it will satisfy some limit condition. So this is, you can define it in a very careful manner. Now, let me do an example, okay? Let me do an example. So this is the kind of function you study in calculus 3, a scalar field or scalar value function. So it's from R2 to R, and then f of x1, x2 equal x1 square, x2. And then how do I find its derivative? According to the definition, I need to consider the difference, okay, between f of x plus h minus fx. Then after you spell it out, okay, this is what you get. And now you try to analyze which one are the higher order terms in h, okay? So higher order terms means those are of degree 2 or more. So in this case, it will be the last three terms. These are the higher order terms. Okay? So as a result, then the first two terms, okay, the h is of degree 1, h1, h2 only, then no product or whatever. So that's why in this example, the derivative, so I write df, and then the variable is x. And remember, this is a linear function, okay? Linear function. And then this linear function is given by the first two terms, so 2x1, x2, h1, plus x1 squared, h2. So this is what the derivative is, okay, in this example. It's a linear map in H, okay? It's easy to check, this is linear in H. But I want to do one thing more. So how do I define derivative? Derivative is defined to be a linear functional, i.e. an element in the dual space of the space of matrices, okay? So since, so let me write it at the bottom. Since dfx, there is a linear map from the space of matrices R is a linear functional, i.e. an element in the dual space, okay? And then one thing you've learned in the before the midterm, the last thing you learned before the midterm is anything in the dual space has a correspondence with the original space, and then that is called Ritz representation theorem. So by Ritz representation theorem, okay, by Ritz representation theorem, every linear functional corresponds to something in the original space, so that exists a unit, let me write a word, that exists a unit G which come from the original space, and as such that what is the relation between the dual element and the original element is that the dual element is itself a function, and that will equal to the inner product of this corresponding element with H. And it is true for all H. So I didn't do anything fast, okay? I just write down what Ritz representation theorem tell me in this setting. So every dual element, okay, and then we correspond to something in the original vector space, and then the relations come from the inner product. And if you recall, what is the inner product we're working here is the Frobenius inner product. So you can write as the trace of G transpose times H. Is how Frobenius inner product is defined. And this g, I'm going to give it a name because this g corresponds to the derivative of f at x, okay? So this g is called the gradient. But now we don't call it gradient vector because g is not a vector anymore, it's a matrix, okay? So I simply call it gradient. The gradient of f at x. And then denoted as, so the standard notation is g equal to the gradient of f at x, okay? So the variable is put at the bottom. And now, so far, it may sound a bit abstract. However, okay? However, if you look back the example above, okay? So we discover the derivative is equal to this linear function over here. And then, what is the gradient vector? Indeed, it's exactly what you did in Calculus 3. Firstly, according to the risk representation theorem, we can write it as an inner product. And in this case, it's very simple how to write it as an inner product. It's just the inner product of 2x1, x2, x1 square, and then with h1, h2. Okay. Then in my definition, which one is the gradient vector? It's the guy in the front. So, the gradient of f at x is given by 2x1, x2, x1 square, which is exactly what we learned in Calculus 3, okay? But at that time, we just give you this weird definition. But now, it's more lateral. It comes from writing the derivative as an inner product and then the first element, or so-called the risk representative under the inner product. So I just want to show you that everything that we've done is consistent with what you learned in Calculus 3. Okay, so it's worth to formulate what I write down here as a proper definition. So let's have a look on the next page. So gradient. So what is gradient? Is suppose you have computed the derivative, and then now by risk representation theorem, the derivative will correspond to some g, and then the g is called the gradient of f at x, okay? So it's called gradient. So in other words, okay, what is the gradient? The gradient is the matrix, the unit matrix that satisfies this relation, okay? So if you write the derivative as a trace, and there's somewhere happening in the front with a transpose, okay? Then this matrix is called a gradient, what? Gradient, okay? We don't call it gradient vector anymore. So we have this fundamental equation, okay? Relating derivative and gradient. But there's something that's extremely unfortunate when I try to look up some reference, because apparently there's some discipline, they don't distinguish the difference between derivative and gradient. But then we do, okay? We're mathematicians, so we're very careful. So derivative is a linear map, and gradient is a matrix, okay? It's a matrix. But one thing that's in common, no matter what discipline you come from, is all of us are very lazy, okay? So we have this fundamental equation that relates the derivative with the gradient, and but it's difficult to remember this in such a form. So, but remember what's h, okay? H is a little bit of change like what you did in Calculus 1, okay? So I think in that time you call it delta x. A little bit of change. So we have a lazy way to help us to remember this equation. So the lazy way is to imagine, think of h as dx, okay? Dx. Because it's a little bit of change in the x direction. Then as a result, we get a equation, okay? And it's not math, it's just a lazy way to write down the fundamental equation relating to the derivative and gradient. And we write it as df equal to trace of the transpose of the gradient and then dx. So it's just a lazy way to remember this, okay? There's no mathematical content of writing this notation. But then it's notation-wise a bit less heavy. And the advantage of this notation is, for instance, okay, again, we interpret it in our familiar case when n is 1, i.e. we're thinking of everything as a column factor, then you don't need to take trace anymore because trace, this is always scalar, so take trace is doing nothing. So you get just this. But if you spell it out, this is exactly what you get coming from the chain rule. So for instance, okay, if you have a kind of function that you learn in calculus 3 like fxy equal x squared y, then what is its differential, okay, df, and then it's just a lazy way to remember the derivative. So, but then in this case it would be the partial derivative with respect to x, so 2xy, and then dx, plus the partial derivative with respect to y, so x squared dy. So just a lazy way to help me to remember the fundamental equality above. We have this topic in calculus 3, but then it's not emphasized, okay? But one thing that is important is, in the previous definition, I can define derivative in all settings, i.e. it does not matter what the codomain is. Because I can define derivative just as the linear terms coming from f of x plus h minus fx. But however, how about the gradient? If you want to get from the derivative to gradient, you need risk representation theorem. So gradient is obtained by applying risk representation theorem. And you can't apply risk representation theorem to all linear maps, but only linear functional. So that's why gradient is only defined when f is scalar valued. You can still define derivative or equivalently differential in a very general setting, but a gradient, because it comes from risk representation theorem, so it only makes sense when your original function is scalar valued. But in contrast, the notion of derivative and differential is just a lazy way to remember derivative, are defined in a more general context. So they make sense for functions whose values are not scalar, but then for factors, matrix, or any other general inner product space. Then the next question very naturally is, why do I care about gradient, okay? Why do I want to know gradient? It's the same reason of why do you want to care about derivative in calculus 1. So in calculus 1, why do you care derivative? Because at a local maxima or local minimum, the derivative must vanish. There is something happening in one variable. But now, when your variable is no longer just a real number, but matrices, then at a local maximum or minimum, then the derivative does not vanish, but then the gradient will vanish, okay? Will become the CO matrix. So that's why we have the next theorem. So if you have a function scalar value, only scalar value function, you can make sense of local maximum and local minimum. And then if you have a point that it gives you a local maximum minimum value, then at that point, its gradient must vanish. Okay, so you plug in the critical point or the local extreme point into the gradient matrix, and then that will give you the still matrix. So far, we have defined differential for scalar value function. Okay, the fundamental equation come from this. Okay, I can't stress. Put star, many star here. Okay, it's the fundamental equation relating derivative or differential with the gradient. But sometimes my function is not a scalar value, so the output is not a scalar, but then it could be a matrix, okay? Then how do I define its differential? So let's have a look, okay? Suppose today you have a matrix A such that each entry Aij is a scalar value function. So you have a matrix such as this, okay? A is a matrix such that each entry itself is a scalar value function. Then in this case, how do I define its differential? It's defined to be the differential term by term, like this. And then a matrix of scalar value functions, sometimes we call it matrix value function. So matrix of scalar function is called matrix value function. So let me do a stupid example to you. For example, dA, A is given by this matrix of scalar function. Then what is dA? It means that you just need to compute the differential entry by entry. For instance, the first entry, if you compute the differential, it will be 2xy dx plus x squared y dy. And then the second one will be e to the x dx plus 1 dy. The third one will be cosine x dx. And the last one will be 1 dx minus 2y dy. That's it, okay? And because you define differential of a matrix value function essentially entry-wise, so standard differentiation will work in this case. So let's have a look on the next page. So suppose today I have two matrix value functions A and B. So A and B are two matrices of function and of compatible size, okay? So when you add them, it makes sense or whatever, okay? Or when you multiply them, it makes sense. And alpha is a constant, it's a real constant, scalar. Then whenever the expression makes sense, then the following rules are correct. Firstly, you have some rule. And then secondly, when you differentiate a product of a scalar at a constant times A, you can take out the scalar. And you have the product rule, okay? You have the product rule. And the next two may look a bit funny, okay? The next one is when you transpose a matrix value function and differentiate term by term, it's the same as differentiate term by term first and take transform. So this is obvious, okay? This is obvious. If you think about how it works, it's obvious. But then the remark I want to make is that because these two are the same anyway, so in the future, I will just write dA transpose. So if I write dA transpose, you don't have to worry about whether I mean dA transpose or D of A transpose because they're the same anyway. And the last thing is about the interaction between taking a differential and taking a trace, okay? So it turns out trace and differential commute. So you can take trace first and then do differentiation term by term, or you can do the other way around. This is also obvious, okay? You take the sum of diagonal entry and then take differential term by term. It's the same as you first take differential term by term of your matrix and take the trace. And the beauty of this subject is we try to compute the derivative of differential, essentially the same thing, of a matrix value function without spelling out the coordinate using these kind of rules. So I'm going to show you a few examples, but before I show you some examples, like this is the fundamental equation, okay? That is about the relation between derivative and gradient. And then in differential notation, that will be given by df equal to the trace of the same gradient matrix. And then dx. So remember, the second line is just a lazy way to remember the first line. And because of this equation, it gives me a very concrete strategy in computing the gradient. What is the concrete strategy? Okay, so I lay out a few steps. Okay, the first step is you have a scalar value function and then try to write as a trace. So because at the end you want to write as a trace, and then you start to take differential and then using the differentiation rule that I have above. And then you use standard property about trace, okay? So what are the standard property about trace that we know? The standard properties include, the first one is trace of PQ is the trace of QP. If they're both defined, okay, of course, okay, if they're compatible and they're both defined, then it's true. And then the second property of trace that we're going to use quite often is when you have a square matrix. Okay, it's fine. If a square matrix A is trace equal to its transpose. Because trace only captures the diagonal entries, okay? And when you do the transpose, it does not affect the diagonal entry of a square matrix. But the point is, then you try to rearrange whatever you get after doing differentiation to write it, okay, write your result in the form trace of G transpose dx. In the form of trace of some matrix dx. Then what is the gradient? The gradient is not G, it's not G transpose, but it's transpose, so G itself. So this is the gradient. Now this is the strategy, okay? Now we go through that, it seems a bit puzzling. But then let me show you a few examples until you get more familiar with what is happening. So let's do our first differentiation, and then but this time for matrix value of matrix domain function. So consider F, the domain is a n by n square matrix, and then to R, then the function is defined by plug in an x, and the output is trace of x squared. Then you're asked to find the gradient. And how to find gradient? First of all, we try to write the function as a trace, but the function is a trace already, so we don't need to do anything. So as a result, we just move on. So df, then of course it will be d trace of x squared. Okay. And one very nice property about differential operator and trace is that they commute, okay? So it's the same as trace of d x squared. X squared is x times x. So I'm just using the fact that trace and differential are commuting. And now you start doing differentiation. X times x is a product. So you want to use the product rule. Product rule, okay? The product rule will give you, this will become the trace of dx times x plus x dx. So I leave some gap, that is intentional, okay? And why do I leave some gap? Okay, because I want to make use of the fact that trace is linear, okay? So trace of haha and cuckoo would be the same as trace of haha plus trace of cuckoo. So that would be the trace of these two terms. And then next, okay, we use a standard property of a trace on the first term. The first term, or you can imagine, is p times q. And the trace of p times q is the same as the trace of the other way around. So we're using, let me highlight that, the whole thing. We're using here the trace of PQ is the same as trace of QP. Then obviously, okay, the two traces now sum up, it becomes trace of 2x dx. It's so fantastic because according to my algorithm or my suggestion, at the end you want to arrange in the trace of a matrix times dx, which is exactly of this form. So we have this guy in the front, but this guy is not the gradient matrix, but its transpose is. So hence the gradient of f at x is not 2x, but 2x transpose. So 2 times x transpose. So wait that. Okay, so this is our first example. The next example I want to demonstrate is what happens if I don't take trace, okay? What if now I only consider f of x equal x squared? Then you can do also the product rule. So df would be, by using a product rule, would be given by dxx plus x dx. Remember, these are matrices, okay? So you can't say that they commute. No, okay? Because these are matrices. Previously, because we're working in a trace, that's why you can flip it around. But then in general, without trace, you can flip it. So we can't simplify any further. So the differential df is just dxx plus x dx. But think about that. What does that mean? Okay, although by differentiation rule is what you get, but what does that mean? So because remember, differential is just a lazy way to denote the derivative. And what is derivative? Derivative is a linear map, okay? It's a linear map. And then, so it's a function in particular. And this function is defined to be, according to what I get above, basically dx means h. So it's a linear map given by hx plus xh. So this is the derivative. So sometimes when you compute something, you got to know what it means, okay? It means that the derivative, which is a linear map, okay? And this linear map is defined by plotting h, I will get hx plus xh. And in this case, there's no gradient because f is not scalar valued. So gradient does not apply here. But I want to emphasize that derivative and differential are still well defined, which are essentially the same thing. One of them is just a lazy notation. So let me do 2 more examples to get you familiar with what's going on. Okay. So next example, try to differentiate the Frobenius law. Okay, or try to find the gradient of the Frobenius law. So what's my strategy? My strategy is firstly try to rewrite my function as a trace. In this case, it's not hard because fx, what is the norm square? Norm square is just inner product with itself. So it's like this. So the first step is always trying to write your original function as a trace. And this scalar value, when you take norm, the output is a scalar. Then now you start applying your differentiation rule. Okay, you start applying your differentiation rule. Then we use our standard trick because differential and trace commute. So you're really just differentiating x transpose x. Then the story is very similar as before. Then you have a product to differentiate, and the only way to do it is by using the product rule. So then we become trace of dx transpose times x, and then plus trace of x transpose dx. Okay. And my goal is to put all the dx at the end. The second term, the dx is already at the end. So the only thing I need to fix is the first term. Then I use the other property that I know about trace is the fact that trace of a matrix equals to the transpose of the same matrix, the trace of the transpose of the same matrix. So once you take transpose, then you will get x transpose and dx. Now, as I mentioned before, I'm not going to write down carefully whether it is dx transpose or dx transpose, okay? Because they are the same anyway. So I just write at dx transpose without bracket. And now you can sum them together. To obtain this, then we will arrange in the standard form. So this guy is not the gradient, but then the transpose which will be a gradient. Okay, so you get 2x. Okay, so this is another example differentiating the Frobenius law. And then let me do one more example, okay? Differentiating a quadratic form, okay? Here, my quadratic form is even more general because it comes from a general matrix. So A is not necessarily symmetric here. And I associate a quadratic form with it by using the standard way, okay, that is f of x equals x transpose ax. Then I want to compute its gradient. And how do I do that? Like as usual, the first thing is try to rewrite this as a trace. Like in this case, writing this as a trace is stupid because this is a real number. And then, so as a result, fx is just this real number trace. Okay? So you don't need to do anything intelligent to turn it into trace. Okay? Itself is a real number, and real number trace is itself. And now you start applying df, compute its differential. I'm going to do it a little faster because I can apply, because the standard way is d trace of this. Then because these two commute, okay, then apply the product rule. So it means the trace of d x transpose times ax. Okay. And then in particular, now I recognize, okay, the term in the middle as a product of two terms. So I start doing the product rule. Product rule. So they will become the trace of, firstly, I have dx transpose times ax and plus the trace of x transpose. A is a constant matrix, okay? So don't worry too much about that. So this is just a dx. So a in the beginning is a constant matrix, okay? So the function does not depend on a is not a variable. And then now what I want to do is put all the differential at the end. In the second term, the differential is already at the end. The first term, then how to put the differential at the end? The way to do it is to use the second property of differential of trace. That is, when you transpose it, you get itself. Too many a. So that's why you get the trace of ax transpose dx. And now you can add the two terms together. If you add the two terms together and a little faster, what you get is a transpose plus a, and then dx. So you will arrange that in so-called standard form. Then now you can recognize where is the gradient. The gradient is not this guy, but it's transpose. So hence, the gradient of f at x equals to not this guy, but it's transpose. So it becomes a plus a transpose times x. So we're done. Okay. So remark, I have 1 minute, so let me do a remark. Remark in particular, if A today is symmetric, then its gradient, because when it's symmetric, that means A transpose is A, so you get 2AX. Okay, so the formula I have here is for general matrices, but in the special case, when A is symmetric, then A transpose is A, so you get 2AX as the gradient. Okay, so let's take a break for 10 minutes, and after 10 minutes, I will continue to do something a little bit more exciting. Okay, so.